Hello and welcome back to ENAE 788M, hands-on autonomous robotics. So let's talk about what is stereopsis or what is stereo vision. So you've seen these guys, this equation, right? So you have your projection equation. You are projecting 3D world coordinates using your key matrix or calibration matrix and projecting into your pixel coordinates, right? But you see there's a term called lambda, which is called the scaling factor, right? So the problem with your monocular vision is you never get depth. It is in some units. This can be 1 meter, 1 kilometer, 1 centimeter. We don't know about it. So that can be anything, right? So that's an ambiguity with monocular vision. So let's say if I have just my standard pinhole model, I can say that my object, if I have this image, I can say that my object is of height h1 and is placed d1 distance away, right? But for the same object, I can say that this object is placed at h2 and placed at d2 distance away. So this is the main problem. As far as this h2 by d2 ratio is constant, I can have infinite of these real world samples which can actually project the same image on the image plane, right? So the problem is your scale ambiguity, like it can be anything, right? So have you guys seen this image ever? So if you like play video games, you can NVIDIA has the stereoscopic image option, or people used to, I think this was about 8 to 10 years ago, people used to use create movies in a stereoscopic image fashion. So you have your red part different and the cyan part different. So it's called a stereoscopic image. Looks something like this, right? You have cyan and red parts. So how do they create this image and how it works for our human eyes? So what they do is you have a stereo sensor. You take two images, like one from the left camera, one from the right camera, right? So what a stereo image camera is basically a set of camera with a known distance or known rotation and translation apart. So you have a camera here, you have a camera here, and you have the relative rotation and translation between the two camera centers. So you take these two images. So once you have these two images, you overlap these, right? Obviously, because there's a disparity or there's a distance between these two cameras, you're gonna see something like this, right? If you project one image on the another, overlay one image on the other, right? So if you do that, and if you have a let's say cyan filter on the first one and the red filter on the second one, you might get the stereoscopic image that we saw before. Like this is what the stereoscopic image would look like. Okay, so how does this work? So there's a hack. What people do is using a 3D glasses, something like this. So one thing, your left eye filters the red part and the right eye filters the cyan part. So because these two colors are at like totally different wavelength in the visible area, so the red part won't will only show the red part, or it is a red filter. If there's a blue light coming, it won't let the red filter won't let it pass through the red filter, basically, right? And same thing for blue filter. If there's a red light coming on the blue filter, it won't pass. So only blue filter or cyan filter will pass only the cyan color, and red filter will pass only the red color, right? So what we are trying to do using this is we are trying to fool our eyes that okay, the object I'm seeing in front of me on the screen is actually 3D, which basically means I am fooling my eyes, saying that okay, my left eye is seeing that object at different position and my right eye is trying to see that object on a different position. Okay, so think about something like this, like hold a finger in front of you and close your left eye and then close your right eye and see the position of the finger. That changes. Like in your left eye it's somewhere here and your right eye is somewhere here on your image plane, right? So that's what we are trying to do. So like you have a stereo eye or stereo vision, right? What you're gonna do is for your right eye you have a cyan filter, right? You're gonna only see the cyan part, which is you have shifted that towards left, or it's towards the left part, and you have another red filter and you have shifted that towards a little right. Then thing we saw in the image before, right? So if we do that, our human eye perceive that, okay, my left and my right eye are perceiving the same thing a little differently. So these two objects have to be at, like I have stereo vision, so these two objects, depending on what the distance between my red and the blue pixel is, I can estimate the depth of that point. For example, this is what I'm going to perceive, right? So depending on how far the red and blue elements are, like the farther they are, the closer the object is. Because if you take this finger and if you, let's say, a mile away from here, even closing a left eye and right eye, I would see almost exactly the same output from my left and right eye closed. So this is what we are trying to do. We are trying to fool our eyes thinking that even that screen in front of us, it's actually a 3D object. So question is, why do we need 3D vision? So this is a monocular camera, right? So in a monocular camera, what we have right here is what we write. So in a monocular camera, we have this particular pixel, which is projected on the image plane, right? Now this particular pixel can have the red, blue, and green values on the 3D world plane or the 3D coordinates, right? The thing is, I just using monocular, I cannot say that, okay, this object is here or here or here, right? If I just follow the projection equation, just we read before, my pixel coordinate location would be f times x by z, and until my x by z ratio remains constant for a different set of 3D coordinates, this equation will hold true. Similarly, I can write it for y. So there's no way using one camera to estimate or say that, okay, this is the correct depth. There's no way, right? So that's why you cannot solve depth using single camera, right? So there will be an ambiguity remain always over there. What if you add another camera? So you have this line, right? You have, okay, these are 3 possible points. Now you have another camera. Now you can draw all these 3 possible points again, right? But here's the catch. Let's say if I know my rotation and translation between the camera centers of my left camera and the right camera, OL and OR the camera centers of left and right. Okay, small p is the point. Now if I can say that, okay, this small p, that projected p, corresponds to the blue pixel. Like if I do feature matching, this pixel and this blue pixel are exactly the same. And if I have this line drawn, I can say that, okay, definitely this is my 3D world point that represents the 3D location of this particular coordinate. So second camera, it's solving the ambiguity, and just using basic triangulation that we studied before, you can actually estimate the 3D location of this point P. Right. So how do people do it actually? So rather than doing feature matching, like detecting features, what people do is they match windows. So let's say on your left hand side you have a window here, right? This window size can be arbitrary or user defined depending on your size of image, right? So let's say you have, for example, for an easy sake, you have a 32 cross 32 window size. Okay, on the right image you have 3 of these windows or infinite of these windows. So this yellow line is epipolar line. Now what you're gonna do is you're gonna make a window here, you're gonna make a window here, and you'll keep making windows here, right? So you're gonna search, okay, which is that window which is closest to this window. This is the main point. So for each pixel in the image or each window in the image, what we are trying to do is we are trying to find first the corresponding epipolar line. So for this pixel, what is the epipolar line in the right image? Okay, once we have this, we are trying to examine all the points on the epipolar line, and finally, okay, I will like for this window, this is the best match for me, for example, right? Now once we have this, that this point corresponds to this point, we can find the 3D world point of this guy using triangulation. Okay, so this is a little complicated if even if we know about RNT or rotation and translation. If the parallels are not if the cameras are not parallel, what we're going to do is we're going to either make it parallel, like at hardware level. So for example, if we have two camera centers like OL and OR, if you have these guys, OL and OR, and they actually lie on one plane, okay, so if you have a parallel camera, the equation becomes much more easier. We'll see how that happens. But if it's not, let's say you have one camera somewhere here and we have one camera somewhere here, and they are on a different plane, so then in that case we are going to rectify that camera. For example, like let's say these are the two imaginary parallel planes, right? And if I had one of my parallel planes here, if I had one of the planes here and one of the planes here, right, these two are not parallel. What I'm gonna do is I'm gonna rectify these two image plane using some rotation and translation. I'm gonna rectify this to this plane. I'm gonna do this for this guy as well. So I will perform a particular r comma t for this guy and r dash comma t dash comma for this guy, so that my rectification of the new planes, which is this, are actually parallel. Okay, so to make it stereo problem easier, I'm want to assume that the camera planes are parallel. If they are not, I'm going to perform some rotation and translation to make these guys parallel. All right, so let's assume it's parallel, and let's assume that the image planes of the camera are parallel to each other, okay, and to the baseline. So the distance between OL and OR you're seeing is the baseline, or the rotation and translation between OL and OR is baseline. All right, so another assumption is your focal length of both the cameras are always the same. Okay, if these two things holds true, we can say that my epipolar line falls along the horizontal lines of the two images. All right, also if I have the known rotation and translation between these two cameras, also known as calibrated stereo pair or known as extrinsics, we can actually solve for our depth using these two images. Okay, so let's see how it works. So before detecting depth, we want to calculate what disparity is. So disparity basically means what's the pixel shift for the same point if I close my left eye and if I close my right eye. So if I close my left eye, I'll see a finger at some point, right? Now if I close my right eye, I see the same finger on another location. So there's a pixel shift between these two, right? So that's what disparity is, how much shift is there. Okay, so just using triangulation or just similar triangles, I can write this equation saying that my shift in my position of this point in left camera and in right camera, the difference between this can be written as this divided by my camera center difference can be written as my focal length by depth, right? So the disparity is defined as x minus x dash that we discussed, right? So disparity x minus x dash can be now written as, so this guy is b baseline, right? This can be written as, disparity can be written as b times f by z. So this is what disparity is. Now the good thing about this is my disparity increases with decrease in depth, right? So notice that it's inversely proportional to depth, and using disparity, if you have disparity, we can actually compute depth. So this is like computing depth from disparity, right? So this is also called like parallax, if you guys have heard before. Okay, so that's why near objects appear to move more than farther objects, right? And if you solve this for sparse data, you will only get depth for these sparse points, or you will get depth at each match features, right? But if you are actually solving it for every pixel rather than every feature point, then you will get dense depth. So imagine you have an image, right? You have second image, If you're actually just doing feature correspondences, you will only get depth for those particular points or those particular feature correspondences. Versus if you want a dense version of depth, right? You will basically do it for each pixel. How we do it is doing window stuff, like detecting, saying, okay, this is a window on the left side. How good or which window is the best match for my left image? Something like that. We'll talk about how it works. Okay, so this is like the basic difference between my my depth computation as a sparse versus my dense map. Okay, so let's say you have an image like this, right? Like this is, let's say, one of the image, or left or right, doesn't matter. So for this image, I have a depth ground truth, something like this, right? Now for the same image, I can say that my window matching algorithm, if I use, rather than just the point features, if I use my window based matching algorithm, then I can compute depth at each window or each point. I will get a result like this. So you notice that is nowhere near perfect, but that's the world, right? You don't have perfect feature matching, first of all, and definitely if you go to window scales, depending on number of windows and what your algorithm is, you can have good or bad results, right? So this is just a result of window based matching. Okay, coming back to how we were doing the matching algorithm. So you have a left window, like you have a window on the left, and you have on the epipolar line, you have a lot of windows on your right. Okay, so windows on the left, and you have, let's say, 3 possible matches for now for right. I want to choose the best one. How do we do it? What is the best match for WL? Is simply this. You have these windows, right? You want to compute the sum of square difference, or SSD cost, for each window, right? So let's say with respect to your left window, for every right window you want to compute SSD. So what SSD does is it measures the intensity difference as a function of disparity, right? So your cost function, or your SSD cost function, would look something like this. So it takes care of your intensity values of this is for the left. So intensity values for this particular windows at each point, right, minus intensity values of the current right window, and these your disparity for these guys, and u comma v basically for that, and doing a square and doing it for each pixel. So this is computed between your left window and one possible right window. So you are going to compute this for each right window with respect to this window, right? So let's say you have a bunch of cost function. And one more thing I want to tell you, that window sizes, the things we are seeing, are user defined, and basically this is one of the most important factor which will make your depth estimation algorithm much more robust. But if you have bigger windows, you have to compute way larger cost function, or SSDs. That means your estimation of this depth will be much slower. So it's a trade-off between speed and accuracy. So the bigger your window is, the worse your algorithm will get, but the faster your algorithm will get as well. So let's say this is the epipolar line, and this is your left image, this is your right image, right? Now I'm literally just, so you see this slit, right? This is one window, this is second window. So I'm trying to do for each and every window, right? There are like hundreds of these windows shifted by 4 pixels or 5 pixels. That's also user defined. So I'm gonna compute my SSD for each point. If I compute SSD for each point, if I plot my SSD between each window on the right hand side and this particular window on the left hand side, I will get an SSD which looks something like this, right? Now this SSD peaks at this particular point, right? So this is my correct window, and now I can say, okay, this particular window matches this particular window, and this is what I want, right? So it represents my SSD scores versus your x-axis. So basically you're shifting your window towards your right side, right, along the epipolar line. So the max of SSD that you are getting in any window is your desired window, or is your correct window, which corresponds to the left frame of this particular window. Now if you have it, you can basically just do a triangulation and find the 3D world location, right? And you are gonna repeat this for all pixels in window. So notice that this particular thing was for only one window on the left hand side. So if you have like n windows on left and obviously n windows on the right, you are computing SSD n square times. So that's why the algorithm is iterative and becomes very slow. So you have to make sure your window size is not too small or not too big. So there's a sweet spot depending on how far the objects are and what's your processor, what's your image size and things like that. So for example, if you have input like this, you have window size, let's say equal to 3. You see it's a sharper image, but there's a lot of noise. You can't understand. Let's say my window size is 20 now. So you see this got smoothened a bit, but it is very important to note that this is a much better representation of depth. Okay, so there's another algorithm called semi-global matching. So it's called as or semi-global block matching. It says SGM or SGBM if you're searching on Python. So this method uses a concept from dynamic programming to optimize a pathwise form of energy function in different directions basically. Okay, so two things we studied, right? Feature-based versus my window-based. So in feature-based stereo matching, it's definitely robust to my clutter and occlusion. So depending on how these objects are placed, are there occluded objects? Is there object one before the other? Things like that. So feature-based stereo matching algorithm is robust to my clutter and occlusion, and it can only find matches at a few reliable points, right? You don't care about the points where features are not good at, for example. So, and it works fine for scale changes and generally wider baseline rather than narrow baselines. So let's say if you have two cameras and the distance between the cameras is small, let's say 3 centimeters is your baseline, which is very small, right? Your feature matching based algorithm won't work that good, because the lower the baseline, the less the disparity in general it is, right? So you want a much more wider baseline to actually find good disparity. So this is a general tip. So one more important problem with feature-based matching, that you only get a sparse cloud of points, not the complete dense map, right? So let's say if you want to move from your feature-based to dense stereo or dense maps, right? So the first thing is we discussed that we extract features when we get a sparse set of matches, like feature matching. Then we are trying to iteratively expand matches to nearby location, which is basically computing SSD and actually comparing all the possible windows, right? Now you use some visibility constant to filter out false matches, like we studied in structure for motion. And then we perform a surface construction that, okay, this is an image, this is an image, I can do triangulation. I can say, okay, this particular window corresponds to this particular window in my left and right camera. Now, if I know the rotation and translation between these two cameras centers, I can say that, okay, this particular point would be at this distance apart, which is basically triangulation, right? So performing the surface reconstruction. Now, the good thing about this is that there's a sweet spot of depth. So each of your camera has some particular field of view, right? So there would be a minimum distance, let's say Z naught in this case. So there would be a minimum distance where you won't have any common field of view, right? So let's say if I put a finger very close to like my nose, right? Closing one of the eyes, most likely I won't be able to see my finger. So there's no way I could estimate depth because there's no common field of view. So it's acting like a monocular camera right now, right? And other thing is, if I'm too far away, like let's say I am about 10 miles away, there's a mountain, right? From my left eye and right eye, I see the mountain exactly the same. It doesn't matter if I'm looking at it from my left eye or right eye, I see that mountain exactly the same. All right. So there's a sweet spot of depth, because if I, let's say, do feature matching for an object which is 10 miles away, the feature matching would be basically identity. Like my, let's say I have a feature at 36,24 in the left frame. In the right frame, I will have the exact same feature at 36,24. So there's no point of feature matching, right? So I cannot compute disparity between these two frames for a very for an object which is very far away. The disparity would be 0. So there's a sweet spot where depth cameras work. So when you're buying depth cameras, just notice that, okay, this is my baseline. Okay, so given the baseline and focal length or field of view, you can actually estimate that how near or how far, or what's the range of your stereo. Okay, same thing if you're creating your own stereo set, this would be the problem. So there are different baselines. So you see the narrow baseline one, and the duo you are using right now is a narrow baseline, and the Tara camera we gave you, for example, was we were actually we were planning to use before, was a wider baseline, for example, right? So another thing is that the algorithms people have developed for wider baselines and narrow baselines are different. Like this doesn't work properly. So narrow baselines are more reliable on relying on more dense reconstruction, because the features are very close. So disparity for features, feature point or sparse data won't work as well as they work on wider baseline. So they have different set of algorithms for narrow and wide, and generally don't work on the opposite domain. So if I have a narrow baseline depth estimation algorithm, stereo depth estimation algorithm, it might not directly translate to my wide baseline. It might not work as well. And same thing if I have wide baseline algorithm, it might not work for narrow, right? So this is the problem with the traditional based stuff. But if I am using machine learning or deep learning, it's much more robust. So there's a paper called Pyramid Stereo Matching Network. So what it does, it given a stereo pair of images, it is computing a much more robust version of my smoothened version of depth, rather than my depth we saw in like window size equal to 3 or window size equal to 30. We see something like this. So these color represents that which object is how much near and how much farther, for example, right? So the objects in blue are, for example, way farther than the objects in green and red, right? So this color scale is a little weird. It's going from blue to red to green to yellow, yellow being the closest one. Okay, so this is a paper, and there's another paper called Learning for Disparity Estimation Through Feature Consistency. If you want to read about these, we'll talk about these things in class, and other deep learning algorithm, that how to compute optical flow, for example, how to compute pose and depth from multiple images and things like that. We'll talk about these things in class, and how deep learning could solve this problem, that okay, my problem between narrow baseline algorithm and wide baseline algorithm, I want one algorithm which works for everything, right? So deep learning kinds of solve this problem. So we'll discuss this in class. So that's it for today. Bye.